Hello, today's video lesson is going to be a more advanced techniques on Lewis structures. I'm going to cover exceptions to the Lewis structure rules, okay, and also talk about resonance structures, and hopefully if there's time I'll get into what's called formal charges, okay? Okay, boron trifluoride. Now if I follow the rules for boron trifluoride, it looks like I should get a structure that has fluorine, fluorine, and fluorine, and I should get a double bond here. Okay, now if you follow the rules that you notice there, look at that, I got a little electron there, it looks like. Let's get rid of that thing. We don't want any sort of confusion later. Okay, so this is what you would get if you follow the rules. You're going to have to remember that boron is a deficient in octet. It will not be able to do this. Okay, if we think about the periodic table and where fluorine is on the periodic table in relation to boron. Okay, hold on a second, I'm going to get a periodic. Right, so now I got my periodic table. So if I look at fluorine here, fluorine is on the right side of the table. It has a higher electronegativity than boron. Boron's way over on the other side. So our electronegativity of fluorine is going to be way higher. So therefore, boron, which is going to attempt to try to create a double bond with fluorine, is not going to be able to do it. Why? Because its electronegativity value is just way too low. That double bond is never going to happen. One little thing about fluorine is it will bond one time, and that's it. Okay, so don't forget to draw your electrons in here. So you have electrons here, 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 here. I'm going to stop drawing all the electrons in just to save some time in the videos, okay? But you should always draw your electrons in. Now, fluorine will always bond one time, one bond, never double bonds, ever. Okay, you're never going to draw a structure where you're going to see fluorine double bonded to anything. So your structure for boron trifluoride would be this, except you're going to put the electrons all around. Okay, so boron and beryllium are going to follow this rule. Okay, just boron and beryllium. Why those two? Again, because in order to get that double bond to happen, boron's going to have to try to pull electrons from these more electronegative elements, and it cannot do it. Now, if it gets further down to the bigger ones, yeah, because the ionization, or the effect, say that again, the electronegativity gets weaker, it's definitely going to be able to pull those electrons at some point, but you're never going to see that. Anytime you see boron, and even beryllium is even weaker than boron, it's going to have a deficient octet. So remember, boron and beryllium, deficient octets. All right? Okay. The other exception to the Lewis structure rules is that we take a look at something like sulfur hexafluoride. All right, I'm not going to go through the steps, but if you try to do the steps and you try to do the calculations, you're going to be able, it's going to say something like 4 bonds. Well, think about it. If I have sulfur and 6 fluorines around here, okay, I'm going to need to have 4 bonds for these 6. So here's where the rules kind of fall apart. So what you're going to have to do is just go back and kind of go to the original rules where you just kind of join everything together and put your electrons on here. More times than not, for these types of structures, you're never going to have, rarely will you have double bonds. I guess they do come up, but if they do, you know what to do to handle. But go ahead and put your electrons in here. I'm not going to do it for all of them, but why is this happening is my question, right? This is what I really want to focus on, is why is this occurring? Well, if we take a look at sulfur in its position on the periodic table, well, it's right here. It's in the 3rd energy level, right? This is the 1st energy level, 2nd energy level, 3rd energy level on the periodic table. Now, what sulfur has going on for it is that because it's the 3rd energy level, it has a d orbital open to it. So not only can it bond and have an octet, but it can actually go beyond the octet, because even though it doesn't use the d orbital in its ground state formation, when it actually bonds and puts atoms together with it, it can then utilize that d orbital. Okay, so this expanded octet, okay, this octet that goes beyond the 8. Now, 8 is not for everything, right? We see it's not for everything. So when we get to expanded octets, we can definitely go beyond, only if it's in the 3rd energy level or beyond. So it has to be 3rd energy level. Why? Because the d orbital is available. So you got to make sure that you mention the d orbital. That's really the crucial part. And why would it be? Because that's where the 3rd energy level starts it. So you can see there are a lot of elements that can actually go beyond the octet rule. I mean, there are. We don't tend to see them too often, but there definitely are a lot of elements that can do that. Okay? So those are your 2 exceptions, okay, to the octet rule. And by the way, with boron trifluoride, it's an extremely reactive substance, extremely reactive because of that deficient octet. And it will react anytime it sees a set of lone pairs of electrons. So it will react with ammonia because it's got that lone pair of electrons on it. We're going to actually see this later on in acids and bases. Okay, so you can see that's, notice that I didn't like that bond there, so make sure it looks like a nice long bond. Anyway, so it sees these electrons, or it's attracted to these electrons. There's going to be a violent reaction between boron trifluoride and ammonia. And even in the water, because water has that lone pairs of electrons on it as well, so you're going to get a violent reaction. So you want to keep this away from any sort of moisture. Anyway, that's a little bit more than you need, but so watch for the deficient octets, watch for the expanded octets, third energy level d orbitals, beryllium and boron for the deficient, and don't forget about resonance. All right, thanks a lot, guys.